So let's talk about the standard atmosphere. Now, the standard atmosphere is a very important concept in aeronautics and in flight simulation. We all recognize that the atmosphere or the weather is different every day, and it varies by location on the Earth, and whether it's daytime or nighttime, different storms passing through. So anyway, it's constantly in flux. So years ago, they came up with what's called the standard atmosphere, and they use this for instrument calibration, and also in flight simulation, you can use the standard atmosphere to model kind of an average of what an average atmosphere looks like above the Earth. And so we're going to walk through that here. So first of all, we're going to start off by treating it as basically a static fluid. So if we say the atmosphere is a static fluid, then the pressure or the change in pressure with altitude, so that's a change in altitude h, and this is what we're going to call geometric altitude, is equal to minus rho, the density, times g, gravity. Okay, so this is just a static fluid equation, and now we can do a few things with this equation. First of all, gravity actually varies with altitude. As you get further away from the Earth, we have Newton's laws of gravitation, and so we can write that G is equal to some G naught, which we'll see what that here is in just a second, times RE, which is the radius of the Earth, divided by the radius of Earth plus the geometric altitude squared. Okay, so the radius of the Earth, we're assuming basically that the Earth is a perfect sphere, which it's not. It's actually closer to an ellipse, and actually it's not even a perfect ellipse. But for our purposes here, we're going to assume that it's a perfect sphere. And that radius of the Earth is kind of an average radius at mean sea level, which is equal to 6,356,766 meters. I'm going to be using the metric system in the units here, but you can also obviously convert this to English units. Okay, so that's our radius of the Earth that we're going to use there, and then this is the gravitational constant. G naught is going to be 9.806645 meters per second squared. Okay, so that's our gravity model, and we're going to plug that back into to this equation here for G eventually. One other thing that we can do with this equation is swap out this definition of density by using the ideal gas law. So if we assume that the atmosphere is an ideal gas, then density is related to pressure from this equation, which you should all recognize. So rho equals P, the pressure, over RT. R is the ideal gas constant for air, and so that is 287.0528 Newton meters per kilogram K. K is the temperature here. So this temperature has to be in K to use this ideal gas constant. And actually, these units can also be written as meters squared per second squared, K. All right, so let's plug both of these in. Okay, so we've got our density equation here, we're going to plug in there, and our gravity equation here, we're going to plug in that. And so we can rewrite this as, and I'm going to move some stuff to the left-hand side. So we'll get RE plus H over RE squared. So I took this guy, which was on the right-hand side over here, and moved it over to the left-hand side of this equation. and then that's multiplied by dp dh is equal to negative p over RT times G naught. Okay, so we have a differential equation here. See, we've got the change in P with H, and we've also got a P on the right-hand side. So this is a differential equation, but we've got this DH here, and we've got an H right here. So actually, you can do this slick change of variables. We're going to define a new variable called Z. Z is what's called the geopotential altitude. Okay, and Z is defined as RE times H over RE plus H. And I won't work through the math here, but it's pretty straightforward. You can simply plug this now into this differential equation and show that this differential equation, then once we plug that in, can be written as dp dz equals negative p g naught over RT. Okay, so the right hand side stays the same, and all we've done is changed this derivative over here. If you just plug this in, then you can rewrite that as just a dp dz. Okay, so now this is easier to solve, and this too is a differential equation. We've got the change in pressure with geopotential altitude, and that's related to the pressure itself. So so this again is a differential equation. Okay, in order to solve this, we have to actually understand how T varies with Z as well, okay? And so this is where we now get into the real definition of the standard atmosphere. So up to this point, we've just, we assumed a gravity model, we assumed it was an ideal gas, but now we're going to actually insert the definition of the standard atmosphere. So we're going to look at on Wikipedia here, and you can just go to this Wikipedia International Standard Atmosphere, and there's this image over here on the right. You can pull up, and it shows you what this standard atmosphere basically looks like as a function of altitude. So so on the x-axis down here, we've got temperature, and on the upper x-axis we have pressure in blue, temperatures in red, and then on the y-axis they have it labeled, that's probably correct, geometric altitude. There's not a whole lot of difference between geometric and geopotential, as we'll see here in a moment, but anyway, you can see that the temperature basically consists of a bunch of straight lines, and this is how they've defined this standard atmosphere. They've taken straight lines and fit it to a temperature profile. And once you know the temperature profile, you can actually, from that equation, from our differential equation, we can back out what the pressure is as a function of altitude. So let's look at what the definition of temperature is here. And again, it's just going to be a series of straight lines, okay? So let's go back over here. And I'm going to insert here, I've typed up this table here that shows you the definition of temperature with altitude. Okay, so now this is in geopotential altitude Z. Okay, so we've got a range from 0 up to 11,000 meters of geopotential altitude. The temperature T sub I is the temperature at the beginning of this region. Okay, so I've got Z sub I is the altitude, the geopotential altitude at the beginning of this region. Z sub I plus 1 is the altitude at the end of this region, okay, or at the upper part of this region. So the initial temperature is 288.150 K, and then Ti prime, this is a slope of how the temperature changes per kilometer, okay? So we've got some temperature gradient here that's constant in this region. Then we get up to 11,000 feet geopotential altitude, and from 11,000 to 20,000, the initial temperature there at 11,000 is this temperature here, and there's no gradient. So actually that temperature is the same all the way through that region, from 11,000 to 20,000. they assume that it's the same. And so then, of course, at 20,000 feet, we're starting off at that same temperature. And here we have a small gradient as we go from 20,000 to 32,000, 1 K per kilometer. And so by the time we get up to 32,000, we're at 228. So anyway, you can see how this is kind of set up as in these regions of constant T prime or a constant temperature gradient, okay? So actually, at this point, we have everything we need to solve this equation. And so we can now solve this equation, and I'll just scroll down here. So what we're going to do is take that equation and integrate it, assuming that temperature is either constant or has a linear gradient, okay? And so what we'll get then is that the pressure at any z altitude, geopotential altitude, is equal to, and we're going to actually get two different solutions here. One for if the temperature is constant within that region, and so if that's the case, then we'll have P sub I, so the pressure, the initial pressure in that region, times the exponent of minus G naught times Z minus ZI divided by RTI. Okay, so this is the solution if T prime in that region is equal to 0, okay? And if it's not 0, then we'll get P sub I times Ti plus Ti prime times Z minus Zi divided by Ti, and all of that raised to the power minus G naught over RTI prime, okay? So this is the solution if Ti prime is not equal to 0. All right, so let me just box this here. So that's our pressure. So we can now compute the pressure at any altitude. So it turns out that as you can see here, what the solution is if I know the pressure, or excuse me, if I want to find the pressure when I'm in this altitude range, for example, between 20 and 32,000 feet, what I need to know is this a region where T prime is 0 or non-zero? Well, this is non-zero, so I'm going to use this equation here. And then I need P sub I, so it depends on P sub I, which is the pressure at the beginning of this altitude region. Okay, so I'd actually need the pressure at this altitude and the temperature at this altitude. Now I've got the temperature at this at the beginning of this altitude, right, at 20,000 feet. But I also need the pressure, and that the pressure at 20,000 feet actually depends on the solution to the pressure from the previous region. So it's the ending pressure, right? And I would have computed the ending pressure in this region based off of the initial pressure of that region, and on back down to the ending pressure of that region that depends on the initial pressure of that region. So I'm gonna run this equation, whichever one of these equations, depending on if T prime is 0 or non-zero. I've got to actually compute it for each of the levels below the altitude of interest. So if I need to know, at 25,000 feet, geopotential altitude, what the pressure is, I've actually got to compute it for this region first, then this region next, and then come up to the 25,000 meters, 25,000 meter mark there. Okay, so I actually have to compute the solution to these previous levels leading up to the level of interest. Okay, because I've got to know the pressure, the beginning pressure in this region. Okay, so that shows that we've got to know some pressure on the ground then. So there's also a standard pressure that we use. That's a pressure at sea level. So I'll call that P0. And that's at at sea level. I'll just put that at sea level. So the standard for that is 101,325 newtons per meters squared. Okay, so I've got to have that so I can compute the pressure in this region, or at the end of that region if I need to go into the next region, and so forth. Okay, so once we have pressure, there's several other things that we can get. So now from this equation, we compute the pressure at any geopotential altitude. And by the way, first of all, the first step in an algorithm is probably to compute the geopotential altitude. And that's based off of your actual geometric altitude. So any algorithm would actually probably accept a geometric altitude, h. That would be used to compute the geopotential altitude, which then would go into this equation here to compute the pressure. And also the temperature. You'd get the temperature from our from a linear interpolation inside of here. I might as well write that down real quick here. So to compute the temperature at any altitude, geopotential altitude z, it's going to be equal to TZI, which is the temperature at the beginning of that region, plus TI prime times Z minus ZI. Okay, so that's just a linear interpolation of temperature in that region. Okay, so once we have pressure and temperature, then another thing we can compute then is density. So density, we can get that from the ideal gas law, and that's simply the pressure divided by R, which we've already defined, and T, the temperature. So that's density. We can also compute the speed of sound. Let me just write these down. So density, we can get the speed of sound. And that is, we usually use the symbol A, and that's equal to the square root of gamma times RT, where gamma for air is assumed to be 1.4. Then we can also compute the dynamic viscosity. And that comes actually from Sutherland's law. Sutherland found that dynamic viscosity is basically independent of pressure and density, but it is a function of temperature. And so for air, the equation that we get is, and actually let me move this down so I have enough room here. So this is mu equals 1.7153 times 10 to the minus 5, and that's in units kilogram per second times meters. And then that is multiplied by T in K divided by 273K, raised to the 3/2 power. And then that is multiplied by 383.4 K divided by T plus 110.4 K. Okay, so that's the equation for dynamic viscosity. And then from dynamic viscosity, we can actually get kinematic viscosity. So kinematic viscosity, spelled that wrong. And the definition of kinematic viscosity, nu, is just mu divided by rho. So it's the dynamic viscosity divided by the density. Okay, and then one final thing here that's kind of interesting to compute is what's called the molecular mean free path. And we usually use the symbol lambda for that, and that is equal to nu, the kinematic viscosity, divided by a, the speed of sound, times the square root of pi gamma over 2. Okay, and again, gamma is that 1.4 constant that we talked about or mentioned earlier. Okay, so this basically defines now our standard atmosphere at any altitude. I'll just briefly summarize. At any altitude, any geometric altitude, we plug it into this equation here to get the geopotential altitude. Then that is used inside of this equation to get the temperature, and inside of this equation to get the pressure. And of course, the pressure depends on the results of the previous levels, because you've got to have this initial pressure for each level, which isn't technically defined in this table here, but so you'd have to compute it for each level leading up to the level that you're looking for. And once you have pressure, then we can get density from this equation, the speed of sound, the dynamic viscosity, kinematic viscosity, and molecular mean free path.